Hello, chemistry, and welcome to section 13.3 and actually 13.4. I will explain why this video is both at the end of this video. So, chapter 13, we're learning about the phases of matter. We looked at the kinetic molecular theory of gases in the first section, and that's the idea that gas is just all these little particles running around bouncing into things. In the second section, we learned at some of the forces between molecules. So some of the reasons why things stick to each other, not how atoms are formed, not how molecules are formed, but how stuff made of molecules is formed. So why certain molecules hang out next to each other in a liquid, or why some don't really hang out with each other in a liquid. And that was with the dipole-dipole forces and the dispersion forces and stuff like that. 13.3 is specifically liquids and solids. And then 13.4 is how to change between those types of phases. And the names you guys will know, like boiling and freezing and stuff like that. But first up, let's look at some liquids. So all the way back in chapter 3, we learned a liquid can take the shape of its container, but its volume is fixed. Okay? So it can take any shape that it needs to, but how much stuff is there, its volume is pretty much fixed. That's why no matter how you hold your water bottle, it's the same amount of water, it's the same height, but it's a different shape because it fits the container. Individual liquid molecules do not have fixed positions in the liquid, but they still need to be by their friends. Okay? So they still are stuck with their friends, but they're not stuck in any particular order. Let's look at these two words, density and compression. At 25 degrees Celsius and 1 atmosphere of pressure, which is just kind of normal temperatures and normal pressures, the density of a liquid is much greater than the vapor of the same conditions. For example, liquid water is way more, 1,250 times more dense than water vapor at 25 degrees Celsius. Even though they're at the same temperature, both gas and liquid particles have the same average kinetic energy. Thus, the higher density of liquids must be traced to the intermolecular forces that hold particles together. Now, liquids can be compressed, but not nearly as much. Gases can be compressed a lot, but if you ever try to squeeze water, it's going to be weird, and you're going to have specialized equipment to do it. You can, but you need equipment to do it. Then we look at this word fluidity. That's the ability to flow. Both gases and liquids are technically fluids. So I know some people say like air is technically a liquid. That's wrong. What they probably mean is air is a fluid. A liquid can diffuse through another liquid as shown here, which means you can drop one liquid into another and they will slowly spread out throughout the rest of it. A liquid diffuses more slowly than a gas does at the same temperature. However, because intermolecular attractions interfere with the flow, thus liquids are less fluid than gases. Okay? Excuse me. Well, let's see, what is this? Liquids are less fluid than gases. The comparison between water and natural gas can illustrate this difference. When there's a leak in a basement water pipe, the water remains in the basement unless the amount of water released exceeds the volume of the basement, right? The water's just going to go into the basement. However, something like natural gas, if that leaks, then that stuff is going to spread throughout the whole house. Okay? So the fluidity of gas is a lot higher. Gas can flow in a lot more places than liquid can. We see here, if there's a break in the gas line, the customer must leave the house immediately because natural gas can explode when it comes in contact with an open flame or spark. So a water leak in the basement, you know that the water is going to stay in the basement. It's going to flow all in the basement, but it's going to stay there. A gas leak in the basement, that's going to spread throughout the whole house. And they're both fluid, but one is more fluid than the other. And if we take this into account with solids, solids are not fluid because if you drop a rock in your basement, it's never going to spread anywhere. It's going to stay as a rock in your basement. It's not fluid at all. But the other ones will flow, will move. will spread out. And this leads us to the idea of viscosity, and that's the measure of resistance to flow. Okay? So things like honey and syrup take a lot to try to squeeze out of the bottle, if it's in a bottle. The reason for that is because they're a lot more viscous than something else. The stronger the attractive forces, the higher the viscosity. Okay? So something water doesn't have a very high viscosity, whereas honey does. If you try to pour both of those out of a cup, the honey's going to take forever to fall out of the cup, and the water's just going to fall out. The same thing with water and oil. Water's not very viscous, and oil is just a little more viscous than water. It just takes a little more energy to stir, or it takes a little longer to pour out. There are some things that could have a lower viscosity than water. Let's see. Acetone. Acetone's has less viscosity than water, which means acetone flows a lot easier than water does. So that's just how resistant it is to flow. High viscosity means it's very resistant to flow. You can think of syrup or honey. Low viscosity, you can think of stuff that flows really easily. You think of water or acetone or something like that. Viscosity typically decreases with temperature, which means the more you heat something up, the less viscous it gets. So that's why if you have hot oil spreads a lot faster than cold oil does. Hot motor oil spreads a lot easier than cold motor oil does, because as you increase the temperature, you decrease the viscosity. As you increase the temperature, you decrease the resistance of flowing. Keeping in line with talking about water or liquids, something else that some liquids have is surface tension. We see, like, in this little cutaway, this water molecule is kind of attracted to these, and this is kind of attracted to these, and they're making kind of like almost little rafts of connected water molecules in a sea of unconnected water molecules. What that kind of does is almost make little little platforms for spiders and stuff to land on, and they can walk on it. And that's why surface tension is a thing, because the intramolecular forces are strong enough to kind of support a little bit of weight, in the same way that like a bridge would. Now, we obviously can't walk on water like that, but something light, like a small bug, can, because their forces are balanced out with the forces of all of this stuff. You and I'm sorry, are a little too heavy to do that. We float because of differences in densities, not because we're floating on surface tension. Now, there are ways to break up surface tension, and that's with the use of surfactants, otherwise known as soap or detergent. For example, if you just take a shower with only water, and you're not going to be able to get a lot of the dirt off of you because the dirt is like non-polar and the water's polar, and we learned that that doesn't work out. That's one reason. Also, because the water can't get everywhere. It's kind of still attracted to itself. So if you want it to get everywhere, you need to break its surface tension so that it flows over everything. And that's what surfactants do. They break the hydrogen bonds between the water molecules and make it a lot easier for all the water to get in where all the dirt is and get that dirt out or off of you. It works with clothing as well. The water will just not get the dirt out unless there's some type of soap or detergent or something in there to be able to break that surface tension so that the water is flowing and getting rid of stuff rather than just hanging out with itself. And because water still likes to hang onto itself, it exhibits a property called capillary action. And this is why on like the edge of a cup of water, it looks like water kind of rises up a little bit. because the water's attracted to itself, but it's also kind of grabbing onto the other molecules of the container. Just a little bit, just enough to kind of hold itself up here. Not enough to completely walk up the side of the container, but enough to make that little oh, I forgot what it's called. Meniscus. The little meniscus right here. Now, if it's super thin, then we can start talking about maybe that water moving all the way up. And that's actually how plants can move water throughout themselves, because there's a bunch of small tubes that the water is able to transport itself up like that. That's also how, if you put a paper towel in just a little bit of water, how the water will go up, like all the way through it. It's because of capillary action. It's because the water can grab onto a bunch of little things, and that can pull his friend up to bring him up, which can bring his friend up, which can bring his friend up, and it's like a bunch of water molecules helping each other out, trying to climb up this paper towel. We see here that's also why diapers can do the thing that they do. They can absorb 200 times its mass in fluid. So if the diaper weighs 100 grams, it can soak up 200 grams of liquid. Oh my gosh, babies. So after this, your book does not actually have a lot. It has this page, and then it's missing the whole rest of this section, and then 13.4. So what I have is a couple videos from outside of the book posted under this video to take the place. So after you're done with this, you're going to watch the next 3 videos, and those 3 videos will account for the second half of 13.3 and all of 13.4. So no more specific videos from me, just this video and those videos below this, and then we will be done with the video part of chapter 13. So make sure to watch those last couple videos.